Alright, we are live. Yeah, good morning works too. It's close enough to morning that I'm happy calling it morning. Let's see what we got going today. Alright, yeah, it is always morning somewhere, which is interesting. I don't think that's always a given, depending on the topology of your planet and the number of suns you have. Anybody here read The Three-Body Problem? It came out a number of years ago. It's an interesting book. It was recommended to me by a former student who rarely recommends books to me, so I took it seriously, and yeah, it was really good. And it's a good geeky story, and it ties into the three-body problem, right, from physics, but also, you know, limits of computation because of chaotic outcomes from changes in initial conditions and all sorts of good stuff. And in that book, it's not always morning somewhere. All right, questions from last time. All right. Well, I'm going to post some homework questions on Canvas to start working on, and since we don't have class on Monday, and I want you to have class time to ask questions, they won't be due Wednesday. They'll be due a week from today, so we'll have plenty of time. But I'll post them on Canvas after class, and if you want to, you know, start looking at them, we can do that. But let me show you basically what I'm going to post. So it'll be some questions from section 1.5, which have to do with summations, right, and nested summations, and so on. And then some questions from the first three sections of our chapter on propositions. So let's take a quick look at those. So 3.1, so 3.1, I'm going to ask you to do question 2, which is basically for each of these statements, identify a simple proposition and then express this by combining those propositions. So what does it mean? The world is flat, or 0 is an even integer. So, you know, we could make a proposition, you know, A, which is the proposition that the world is flat or 0 is an even integer. But if we're trying to do proofs and we're, you know, using propositional variables to define various statements, the smaller the propositions are, usually the more success we're going to have in working with those. So rather than make a proposition which says, you know, all of this, right, we would probably make two propositions, one which says the world is flat and the other which says 0 is an even integer. And then this proposition stated here in question A would be, you know, that first variable or the second variable. So it would be a disjunction of two variables. So that's what you want to do for these questions, is write this as a logical statement involving, you know, propositional variables that you define, and then it asks you to tell whether the proposition is true or false. So that's getting some practice with you know, writing and working with propositions. And then 3.2, question 2. So this is going to ask you to write some truth tables, right? So this is kind of a rehash of Engineering 250, but you can think of it in the scope of propositional logic. And then 3.3, we've got a few questions, and we may or may not get to everything we need to do these first. Question 2 is a truth table question, and so these involve implications. So, you know, the arrow that we're going to start today by talking about. give a proposition generated by P, Q, and R that's equivalent to this. So we'll be talking about equivalency between propositions. And then this is another question about equivalency and good old De Morgan. So, so we'll talk about conditional statements more right now, and we'll talk about equivalency of propositions. We won't actually have homework questions on proofs for this next homework set, but the one after that, we'll start digging into proofs, and that's where the good stuff starts to happen. So. All right, that's okay if you're late. As long as you're here, it's good. All right, so let's continue making propositions from other propositions, and towards the end of the class, we'll change gears, and I'll go back and talk about some weird things from set theory. But let's keep making progress in propositions. So. We ended Wednesday talking about this conditional statement, this idea of if P, then Q. Yeah, don't you love Windows updates, especially when it's like, when would you like to update? And you start typing it in, and suddenly it reboots on you. And that's always good. So if P, then Q. And the part that we ended with was looking at the truth table for this, and the truth table is potentially confusing. Because this proposition is almost always true. It only fails to be true if the hypothesis is true, but the conclusion is false. And that's really the essence of what this if-then says. What it says is, if this is true, then that is true. And so the only time this fails is if this is true, but that is false, which is this third row of the truth table. So if the hypothesis is true, the conclusion must be true. So this is true, it's got to be true. Up here, the hypothesis is not true. It doesn't matter whether the conclusion is true or false. The conditional is still true. And so that's you know, potentially disturbing, because then you get into these things that I said last time, like if 1 + 1 = 3, then time travel is possible. And whether time travel is possible or not, that if-then statement I just made is absolutely true in the realm of propositional logic. All right, so so let's play around more with this. So given the proposition and I'm just, you know, assuming I've stated here P and Q are propositions, right? So given the proposition if P then Q, we can define some new propositions. One would be if not Q, then not P. And this is called the contrapositive. So this is the contrapositive of that statement. We could also write the statement if Q then P. This is called the converse. And we could also write if not P, then not Q, and this is called the inverse. So you definitely want to know these terms. If we start with a proposition if P then Q, we can define the inverse, the converse, and the contrapositive of that original position, that original proposition. All right. Well, these are interesting to explore. So let's put some conditions, some specifics on here. So let P be the proposition. Today is Friday. And let Q be the proposition. We have CSE215 today. Yes, I do / when I write comments to myself now. So it's not just you. Sometimes I do number signs. It depends what courses I'm teaching. All right. So in words, this says if today is Friday, then we have CSE215 today. And since we're in this class, we hopefully all believe that this is a true proposition, at least for the next few weeks. All right, so let's look at some variations on this. If not P, then not Q. That's the inverse. So what does this say in words? Somebody tell me on microphone or in chat. Not P implies not Q. If today is not Friday, then we don't have CSE215. And is that a true statement? If today's not Friday, we do not have CSE215. Hopefully that's not a true statement, because we also come to 215 on Mondays and Wednesdays. Although maybe that's why the numbers are dropping. Alright, so if today is not Friday, and that's false. So even though P implies Q is true, in this case at least the inverse is false. Oh, you're going to Morgan's theorem with 3 variables in chat. That's awesome. Alright, so this example right here is enough to tell us that the inverse is not logically the same as the original. It's not the same meaning. But this is a mistake in logic that a lot of people make. Right? A lot of people, if they know P implies Q, well, if P is not true, they assume Q is not true either. And that's not logically correct. Every example I can think of is political, and I don't want to go political on us here. Let's see. If you ask for seconds, then you must really like my cooking. Right? And that's a true statement. I wouldn't ask for seconds otherwise. If you like seconds, if you like my cooking, you're going to ask for seconds. Sorry. If you ask for seconds, you must like my cooking. You don't ask for seconds, therefore you don't like my cooking. Right? It does not follow. Yeah, politics is easier. Um, if you put a flag in front of your house, you love America. You don't have a flag in front of your house, therefore you don't love America. That does not follow logically, right? Maybe you're not allowed to put a flag in front of your house. Maybe you don't have a flag, right? Or you could just be full and you don't want seconds. All right, so the inverse is not the same as the original proposition. What about the converse? So Q implies P says, if we have CSE215 today, then today is Friday. Hey, there we go. There's a good non-political example. If I paint my house yellow, then it means I like yellow. I didn't paint my house yellow, therefore I don't like yellow. Could just be you didn't want a yellow house, or you didn't have yellow paint. Awesome, thank you. All right, so if we flip these around, that's the converse. And the converse here says, if we have CSE215, then today is Friday. Well, that's also not true, right? Because on Wednesday, we have CSE215, but today is not Friday. So this is a false implication. So this is also not logically equivalent to that. But it's still another common fallacy that people make when they think they're trying to argue things logically. So, let's see. So if it's sunny outside, then I will go for a run. I'm going for a run, therefore it must be sunny outside. Well, maybe I run every day, regardless of whether it's sunny or rainy, right? All that this says is if P is true, Q is true. But if Q is true, we don't know if P is true or not. And all I can think of is even worse political examples for this one. Trying to think of like common fallacies that people brush up against with this. Right? If you give me $100, then you must really be my friend. If you're really my friend, then you're going to give me $100. Those are two different things, right? Let's say it's true that if you give me $100, you must really be my friend. Well, that doesn't mean that if you're my friend, you're going to give me $100, right? That doesn't follow logically. Yeah, because we could just keep invoking that. All right. So let's look at this third example, which says not Q implies not P. That's the contrapositive. So someone tell me what that translates to in words. Yeah, if you comfort me in a difficult time, you're definitely a friend. That's a good definition. Alright, so what's if not Q, then not P look like? If we don't have CSE215 today, then today is not Friday. Right? That's not Q. We don't have CSE215 today. Then not P. Today is not Friday. I know what you meant. So is this true or false? Suppose you wake up and you check your crystal ball and you say, you know, do I have CSE215 today? And it says, no, you don't, right? It can't be Friday. Because if it was Friday, you'd have CSE215 today. We're not worrying about holidays. That changes everything. So if you don't have class today, it cannot possibly be Friday. That is logically equivalent to the statement that if it is Friday, you have class today. And the reason we're ignoring holidays is because we're assuming that this implication is true, which means simply any day that's Friday, we have class. So this turns out to be logically equivalent to that. And sometimes when we're trying to prove something like if P then Q, it's going to turn out to be easier to prove if not Q then not P. And once we've done that, we know that this is logically equivalent to that, and so if we've proven this is true, we'll be able to conclude that this is true also. And that's the whole motivation for the contrapositive. Because the contrapositive will end up being logically equivalent to the original proposition. And it mostly makes sense if you think about it. Right? If P is true, then Q must be true. So if Q is not true, P simply can't be true. Because if P was true, this says Q would have to be true, but you already told me Q wasn't true. And we're going to spin a number of webs around this idea of a contrapositive. This is going to lead to a type of proof that we call an indirect proof, or a proof by contradiction. And those things are really just proofs of the contrapositive of some statement. So, question in chat, does a proposition always need to be true, or can it be true over a given reference? So in this course, we're going to sort of sweep that under the rug. And, you know, if I tell you that, you know, this is P, this is Q, and if P then Q is true, we're going to assume it's absolutely true, right? It was true before, you know, there was life on the planet, and it will be true after our sun goes supernova, and still, you know, every Friday we'll have CSE215. So it's a sort of more theoretical version of this, but that will simplify things. But you know, in practice, there's a lot more we would put. If today is Friday and it's not a holiday, and it's sometime during, you know, winter quarter, then we have CSE215 today. So we could quantify it like that. Yeah, what if Dante's Rings is actually like CSE215 class? And you like gotta go hang out there with Virgil for a while. All right, so these we're going to talk about from time to time in the realm of fallacies, right? Logical errors, things that do not follow from original proposition. Contrapositive we'll talk about in terms of proofs, because sometimes we prove the contrapositive, and that gets us back to proving the original statement. And let me mention one more variation on all of this. Which is P and then this double-headed arrow Q, which we call the biconditional. Yeah, that's Dante's Inferno. So P implies Q, and also Q implies P. So we can think of this as a conjunction. That looks like that. And so this would say, today is Friday, if and only if we have CSE215 today. Or we could say, if today is Friday, then we have CSE215. And also, if we have CSE215, then today is Friday. So it's the conjunction of a conditional and the converse of the conditional. And we can think of this as if and only if. And it really says that these two things are true or false in unison. If P is true, Q is true. If Q is true, P is true. And so equivalently, if P is false, Q is false. And if Q is false, P is false. All right, good with these? Because we're going to go on, we're going to look at truth tables for these. And is someone trying to ask a question, or was that just an unmute? I can hear audio, I think, but I'm not hearing any audio. Okay, so, well, I saw someone's mic on for a minute. So somebody turn your mic on and try talking. And I see your microphone symbol moving, but I'm not hearing anything. So let me check my audio. I am connected. I have volume. All right, let me do this. Let me stop my share. Oh, I can't stop my share, so my Zoom is misbehaving. I was going to stop my share and then go in and reset my audio. Let me try this. Alright, my speaker works. So try talking again.
Test.
Oh, there you go.
Yeah, I am.
Okay.
Nice.
So sometimes with Zoom, it seems you have to go and test your audio, and that makes it start working, even though you don't change anything. But I still can't stop my share, so if anything else weird is happening, let me know. All right, so I haven't heard any questions anyone has said, so if you had questions, go ahead and please ask them again. You can't see my screen. Okay, so I guess the stop sharing worked, but it didn't tell me it stopped sharing because it's still showing me as sharing, which means I can't start sharing again. So, let's see. All right. I'm going to have to end this meeting and restart it then. So all of the chat session will go away. All right, so let me end the meeting. I will start it right back up, and please go ahead and reconnect, and then we'll talk about not P, not Q being biconditional. All right, so hop right back in, please. People hopping back in.
Can you hear our
I can hear you. It's a miracle.
Nice.
Yeah. And I'm guessing you can hear me since you responded. Now, let's push our luck. Let's see if I can share my screen.
There we go.
All right, awesome.
You have audio still?
Yeah, I can hear you. Can you hear me?
All right. Yes.
Cool. All right. Well, that was exciting. That was our chance to stretch our legs.
I think I know what I did wrong, or didn't do wrong, but so I had bookmarked the URL given in the Zoom meeting info from Canvas, and I joined the meeting through that bookmark URL instead of going through Canvas first.
Okay, that should work normally.
Yeah, the problem was on his side, not yours.
Yeah, I was having a problem on my side.
My bad then.
No problem. All right, so this is the biconditional of P and Q, right? Which basically means P implies Q and Q implies P. And if P implies Q, we know that the contrapositive tells us that not Q implies P, implies not P. And if Q implies P, that tells us not P implies not Q. And this is really just the definition for not Q if and only if not P. So this and that will be equivalent to each other. Five frames per second on Zoom. That's not good. Somebody was telling me that Zoom just got like adopted by some other entity that was using it for some large scale setup, and that might be dragging things down. I don't know. I just know this has been a bad week for me for Zoom. All right, so let's look at truth tables for these different kinds of conditions. So as usual, P and Q are propositions, and there's 4 possibilities. And we'll start with the straight conditional, if P then Q. And we've said this is true except when the hypothesis is true and the conclusion is false. Oh yeah, don't say teams. All right, so that's the conditional. So what would the converse look like? Well, we can fill this in from the table, right? This says if Q then P, and we know that's going to be true. If Q is false, so here and here, and it's also going to be true if Q is true and P is true, so it'll be true in this case. But it will be false when the hypothesis is true, that's Q is true, but the conclusion is false. So it fails to be true in this one case. All right, so that's the converse. The inverse says if not P, then not Q. So this will be true as long as not P is false, which means anywhere that P is true. So it'll be true in these cases. And it will be true if the hypothesis is true and the conclusion is true, which means P is false and Q is false. So that's true over here. Nope, this can't be right because I'm getting the same truth table. Yeah, that's fine. But then it's false in this case. And then contrapositive is not Q implies not P. And so this is true if the hypothesis is false, meaning Q is true. So it's true right here and right here. And it's also true if the hypothesis and conclusion are both true, meaning Q and P are both false. And it fails to be true when the hypothesis is true and the conclusion is false, meaning Q is false and P is true, and that's this row right here. Q is false, P is true. And then the biconditional, well, this is a conjunction of P implies Q and Q implies P. So this is true whenever both of these are true. So it's true here, and it's true here, and it's false in those middle two rows. Yeah, and these don't impart a lot of insight just by looking at them because, you know, it's just a bunch of T's and F's. But some things to note here. First of all, this column and this column have exactly the same truth values everywhere. Right? That's the sense in which this and that are logically equivalent. Because remember, this is saying, you know, if I pick a value of P for which P is false and I pick a value of Q where Q happens to be true, right, then this is what the value of each of these propositions will be in that case. Well, when two columns match in all rows, right, when they're exactly the same, it means whatever values you pick for P and Q, whether they end up being false and false or true and false or whatever values you pick for P and Q, this proposition and that proposition will have the same value. And the same thing can be said for the converse and the inverse. Those always have the same truth value as each other, so they are logically the same thing. And that makes sense because this is the contrapositive of that. And we just said contrapositive is logically equivalent. Q implies P, the contrapositive would be not P implies not Q. Well, that's this right here. Now, the biconditional doesn't really match up with any of these things. I mean, it's the or of these. It's also the or of the inverse and the converse, right? The disjunction. But if we look at this just as itself, this is true whenever P and Q are the same. So this is telling us that P and Q are simultaneously both true or both false. If that's the case, then this biconditional is true. That's why we think of this as an if and only if. If P is true, then Q is true. If P is false, then Q is false. If we want to throw in a little nod to 250, this is an exclusive NOR function. So exclusive NOR is, right, an XOR followed by an inverter basically gives you equivalence of the inputs. If your inputs are both zeros or both ones, an XNOR will be a 1. And if they're different, if one of them is a 0 and one of them is a 1, then it'll give you a 0. There is no exclusive AND that we normally talk about. What if the P and Q in the biconditional are not P and not Q? Same thing. So, right? This would mean that this is true and that is true. right? So we're looking at not P implies not Q, and also not Q implies not P. And they're both true here, and they're both true here, and one of them fails to be true in those two cases. Now this doesn't impart a lot of warm fuzzy, you know, insight, but this is kind of the rigorous, you know, analysis of what's going on with these derivative propositions, and we can always come back to the truth table to, you know, do proofs of things or to answer questions about, you know, is this the same as that, and so on. But this doesn't really work with our usually our logical thinking of propositions and propositional statements, right? We usually think of it more, well, logically, right? So it's like when you design a circuit on a circuit board, you're not really thinking about truth tables, you're thinking about logic gates, right? But to get there, right, this has got to be underneath at some level. So we'll come back to these sometimes, and we'll use them to answer questions, but mostly we're not going to be working with truth tables in this course. We're going to be working kind of at a higher level with the propositions themselves. Okay, so this gives us the idea of propositional equivalence. I should be tagging these. We got some action commentating going on.
Task force.
Yeah. Oh, there we go. Okay. Possibly the most exciting part of the class. I don't know. Propositional equivalence. So this is basically saying that two propositions always have the same value. They could always be true. They could always be false. They could be true or false depending on the values of the variables. But two propositions are equivalent if they always have the same value as each other. All right, and we write this by saying 3 lines, and this means P is equivalent to Q. And so we could restate what we just said a few minutes ago. And say, you know, if P then Q, that proposition is equivalent to if not Q then not P. Something's going on my CPU because my fan is about to like take off, and I'm getting like package temperature warnings on, oh, they're back to normal. Nope, they're going up on some of my CPUs. I don't know what's going on. I'm thinking it's Zoom. So if I burst into flames, that's probably the end of the lecture for today. All right, so propositional equivalence, right? Two propositions that always have the same truth value. There are two particular equivalences that we can talk about. The first is called a tautology. So proposition P is a tautology if P is logically equivalent to true. And P is a contradiction if P is logically equivalent to false. Alright, so these are definitions. We're talking about a proposition P. We can call it a tautology if it's logically equivalent to true. Well, what does that mean? It means that whatever the value of your propositional variables, this proposition is true. So I'll give you an example of a tautology. P or not P. This is guaranteed logically equivalent to true. The triple equal sign is equivalence. The reason this is a tautology is because it does not matter what the proposition P is. It could be 1 plus 1 equals 2, it could be 1 plus 1 equals 3, it could be the moon is made of green cheese. Whatever proposition P is, this is guaranteed to be logically equivalent to true. So that's a propositional equivalence. That's a tautology. Propositional equivalent to T. And so P or not P is a classic example. Triple equal sign it's not an underlined equal sign, it's a triple equal sign, it means equivalence. In Word, is there a triple equal somewhere? Yeah, there is. You have to work for it. But it's in there somewhere. The V is a disjunction, so it's a logical OR. And the caret is a conjunction, which is a logical AND. And the hook is a negation. Alright, so this is also a tautology. Either A and B are true, or A is false, or B is false. Or not A is true, or not B is true. Thank you. All right, so how do we show that these things are tautologies? Well, we can go back to truth tables. So let's make a truth table for P. And let's fill in the possibilities for not P. So P is either false or true, which means not P is either true or false. And so P or not P is just the disjunction of these two columns. Well, false or true is true, true or false is true. And so this is logically equivalent to true. I mean, we could write a truth table for true, and that's just got a true in every column. If we do this other example, so A and B, or not A, or not B. Well, 4 possibilities. So A and B will mostly be false, except down here. The negation of A will be true, true, false, false. The negation of B will be true, false, true, false. And so if we take the disjunction of those three, well, we're looking at the OR of these three columns, so this is certainly true. There's a true in there, so that's true. There's a true, so that's true. There's a true, so that's true. And this has exactly the same truth value as true, so this is logically equivalent to true. And yet, if you're going to try to typeset some of the stuff, it's a good excuse to learn LaTeX. Because LaTeX, all of this stuff is easy to write. So like someone said, \equiv for the equivalence symbol. And there's \right arrow and cup and cap and all of those things. All right, so those are tautologies. Contradictions are logically equivalent to false. So for example, P and not P. That's a contradiction. And this is kind of the quintessential contradiction, because when we learn to do proofs in this class, we're going to write our proofs as a series of propositions, each of which should be true, which means everything that we've written, since each of those things is true, the conjunction of all the things we've written is also true. And in our proofs by contradiction, we'll have some proposition P, and later on we'll prove not P. And so we'll know that both P and not P are true, and we can use that to say, well, that's equivalent to false. And so we've got a series of statements that are true, but one of those statements is actually also going to be false. And true is never equal to false. So that'll be our contradiction. We'll see that in more detail when we talk about proofs. Is that probably the best way to type this stuff up, or is there something else you would use, Nick? I like LaTeX. I mean, LaTeX is beautiful. It's been around forever. I have documents from the 90s I wrote in LaTeX that I can still render today, just with, 3 commands. And render is a typesetting system. Word is not, right? Word is a word processor. It's a way to move text around. And then you can, make things boldface or change the font or the size or the spacing and stuff like that. Tech and LaTeX are text processing systems. They are built up on top of the idea of taking little wooden blocks with letters on them and placing them in a print box, right? And when Knuth developed Tech, he was making a computerized version of how typesetters actually place the print blocks in a box to render a page with ink, and it builds on top of that. It's relatively tiny. It's a big subject to learn, but you don't need to know most of what's involved in LaTeX to use it efficiently. But it's a markup language, right? Which can be nice because it's very stable. And it was developed partially when physicists were starting to collaborate over the early days of the internet, right, back when it was ARPANET, and they wanted to share preprints of their papers, and so they wrote these papers up in ROF and TROF and stuff, and eventually LaTeX or Tech at the time. But you can save these and store them and share them as just plain text. It's not some weird binary file, and Word uses XML now, so they're finally at that point. But yeah, LaTeX is a great way to go, and the documents you get out are beautiful. If you look at a document produced on LaTeX, you can tell right away. And you can take the same document and you can write it up in Word and you can write it up in LaTeX, and it's totally obvious once you've looked at these which one came from which. Word is getting better. But I mean, that's what LaTeX is for. Yeah, it looks professional on resumes. I used LaTeX for all the document preparation for my tenure stuff, and actually got comments on that from people. It's just a nice touch. And some teachers at a university will possibly insist on that. So LaTeX is a program. You can download it on Linux. It's all, you know, freely available. And you have to figure out the hoops to jump through, but mostly you do LaTeX on a .tex file. And it creates an output like a DVI, device independent, and then you run that through something that turns it into PostScript or a PDF. Last sales pitch about LaTeX. LaTeX is really about letting you manage the content and letting this tool manage the formatting. So you say, you know, here's what I want my document to look like. I want this to be a format that's acceptable for IEEE transactions. And I want 2 columns per page, and I want my bibliography to use this kind of style. And you set that up, and then you just write the content. Right? And you don't worry about, you know, oh, I've got to add another sentence and now my picture has jumped to another page and I have a big empty gap at the bottom of this page, right? You don't deal with that. You let the software deal with it. You just write the content. And if you have to change the content, you go in and you change the content. And it will render, you know, this beautiful document for you based on the specifications. You can run it on Windows. There's also a GUI version that I'm learning to like a little better, called Lyx, L-Y-X, and it's a WYSIWYG front end to LaTeX. Definitely takes some getting used to, but I'm less at the point where I'm happy to like spend a lot of time writing all this stuff up by hand and relearning LaTeX because I use it so infrequently now, so that's not bad. All right. So we can write logical equivalence signs. Let's see. So let me show you one other logical equivalence that will come up a lot. Now this is good stuff. I mean, it's all computer science, and you know, we should talk about it somewhere. So I'm happy to go over pretty much anything. So if P then Q is this mysterious conditional statement, right? It turns out that's logically equivalent to a perhaps less mysterious if not P, or not P or Q. All right, well, why is that? Again, this doesn't always impart great intuitive understanding. But here's what not P looks like. Here's what Q looks like. If we just take the disjunction of those, and I'll add extra parentheses here just to be clear. If we take the disjunction of these 2 columns, that's true, true, false, true. And so here again, this column and this column, exactly the same truth values everywhere, true, true, false, true. That's our kind of proof or demonstration that these are logically equivalent. But the way to think about this maybe in words, if P then Q, well, this is saying, you know, either the hypothesis is false or the conclusion is true, right? And we've already seen if the hypothesis is false, the conditional is true. We don't care about the conclusion. But if the hypothesis is not false, then we need the conclusion to be true. And so this is the same as that, and we can use them interchangeably. All right, so let's talk about identities. So we can write a number of statements using these propositional concepts. So for example, P and true is always going to be the same thing as P. Because if I take, I'm asking, is P true and is true true? Well, we know T is always true, so the logical value of this is really just the logical value of P. So this will always have the same expression, the same truth value as just P. And similarly, P or false is always the same as P. P and F is always false. P or true is always true. P or P always has the same truth value as P. P and P always has the same truth value as P. The negation of P always has the same truth value as P. P and Q always has the same truth value as Q and P. P or Q is the same as Q or P. P ANDed with the truth value of Q and R is the same as P ANDed with Q, and then that truth value ANDed with R, and the same with disjunction. And these look familiar to anybody?
Similar to that of the set identities.
Yeah, very, very similar to the set identities, and very, very similar to Engineering 250. Right, someone said 250 in chat. This is totally parallel. And so we get good old De Morgan in two versions. And someone said P times 1 equals P, so that would translate to P and true is equivalent to P. So that's the same as this first statement. So P and not P is always false, because something that is true, if P is true, its negation can't also be true. And P or not P is logically equivalent to true. And one more pair that's sometimes very useful. P or P and Q is logically equivalent to P. And P and P or Q is also logically equivalent to P. So what's going on over here? If P is true, then this whole expression is true. If P is false, then this part of the expression is false. But if P is false, this part of the expression is also going to be false. And so the whole thing is going to be false. So this is logically equivalent to P. And you can do the same kind of argument here. If P is true, then this part of the expression is true, and if P is true, P or Q is true, so this part's true, the whole thing is true, this is true. And if P is false, then the AND has to be false, because anything ANDed with false is going to be false. So you can find these basic logic laws on page 58 of your textbook, and they have fancy names like involution and absorption and idempotency and all this kind of stuff. But these are things that we'll use a lot. You don't need to memorize these names, but put them on your note sheets so when you're writing proofs you can refer to them directly. But these are fundamental laws of logic. And the following page 59 will have these implications that we'll use when we start doing proofs. So if we were meeting in person, this is where I usually hand out a sheet of paper with these 2 pages on both sides of it, and I say keep this with you at all times, right? Because we'll just use this a lot in chapter 3, but also a lot of the other stuff that comes on later. So bookmark this or download it as a 2-page PDF or something. Page 58 and 59 from the text will definitely come in handy. On the negation law, why did P become uppercase? It's an open source text, so it probably didn't go through a lot of editorial review. But yeah, that should be a lowercase p. Nice catch. You want to see typos, look at my C book that I wrote. That is like filled with typos because, I had like a week to write it. So, all right, let's see. Yeah, no, it's good. It's good to mention those things. All right. So the next step would be to look at how we can use some of these laws of logic to do proofs, right? We know how to use them in truth tables, but to put together proofs, I'm going to leave that for now. I'm going to leave that for now, and we've got 15 minutes left in class. So let me switch gears here. Yeah, kind of story time. Not quite, but let's talk about some weird stuff. All right, so we talked about cardinality our first week, and this idea of sizes of infinity. And I made this claim that the size of the set of real numbers was somehow fundamentally bigger than the size of the set of integers. Now, when two sets have the same cardinality, what we're saying is we can find a function between the elements of this set and the elements of that set, which is one-to-one and onto. In other words, there's a one-to-one correspondence between things over here and things over there. Okay? So this is our basic definition for the next 15 minutes. Two sets have the same size, the same cardinality, if we can find a one-to-one mapping between the two sets. So to say that something has the same cardinality as the integers means we can find a one-to-one mapping between that set and the set of integers. So let me start off with the set of positive integers. And I claim the set of positive integers is exactly the same cardinality as the set of all integers. Even though the set of all integers has, roughly twice as many things in it, they have the same cardinality. And all I have to do is tell you what this one-to-one mapping is between those two sets. Well, so I'm going to take 1 and map it to 1. I'm going to map 2 to -1. I'm going to map 3 to 2. I'm going to map 4 to -2. I'm going to map 5 to 3. I'm going to map 6 to -3. And so on. And that's my one-to-one mapping between the set of positives and the set of all integers. Oh, I forgot 0. Okay, we'll do it like that. Oh, nope, I did that wrong too. Alright, there's a mapping. So over here I have all the positive integers. Over here I have all the integers, positive, negative, and 0. And it's a one-to-one mapping. Each integer here corresponds to one integer there, and vice versa. And this should pretty clearly be the set of all integers. Because eventually, if you think of the number 500, well, I'm going to find that the number 1000 maps to 500. And if you wanted -500, well, the number 1001 would map to that. So this is a one-to-one correspondence between the things here and the things here. And that's all we need to show that these have the same cardinality. And this is a particularly nice fact because this is the numbers we count with. So any set that we can count, in other words, any set that we can identify, this element is 1, this element is 2, this element is 3, this is 4, and so on, and by starting from 1 and counting up, cover every single element in that set, such a set's going to have the same cardinality as the set of positive numbers. So if we can count the elements of S, then the cardinality of S will be the same as the cardinality of the positives. And since the cardinality of the positives is the same as the cardinality of the integers, then the cardinality of S will be the same as the cardinality of integers. Quick aside, what would the stuff on page 58, 59 be called? I don't know, I would just call it like rules of logic. They actually have titles in the text. The first one I think is called logical laws, and the second one is logical equivalences or something like that. It's in the top of the table. All right, so we actually have a term which is a set S is called countable if it has the same cardinality as the integers. And so the set of prime numbers is countable because we can identify a first prime, a second prime, a third prime, a fourth prime, and as long as you know that there's no limit to the number of primes, there's an infinite number of them, it's a countable set. The set of even numbers is countable because we can say the first even is 2, and then 4, and then 6, and then 8, and then 10. So the positive even numbers is a countable set. And so any set that we can arrange in some way that we can count and identify the first, the second, the third, the fourth element is automatically equivalent to the set of integers. And so if we take the set of fractions, right, the set Q, we can ask, is that bigger than the integers? And it turns out the answer is no. So I can create a table and we'll just worry about positive numbers for now. And if I keep continuing this table out, any fraction comprised of a positive integer divided by a positive integer will be somewhere in this table. Right? The number 17 over 5 will be in my 17th row in my 5th column. So if we just think about positives, right, every fraction appears in this table somewhere. And in fact, some fractions appear more than once, because this is the number 1, this is also the number 1, this is also the number 1, this is a half, this is also a half. So this is actually more stuff than the set of all rational numbers. But we can still show that this is countable, that it's got the same cardinality as the integers. And the way we do that is by just finding a way to number the elements in this set. So we're going to start with this element, and then we're going to go to this one, come down on the diagonal, move down one more, move up the diagonal, move across, move down, come down, move up the diagonal, move across, come down, and so on. Nope, I forgot to move down. And we associate each number with its position along this path. So this is mapped to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and so on. And that's a one-to-one mapping between the set of positive integers and the set of positive rational numbers. And so that's enough to show that the cardinality of the rationals is the same as the cardinality of the integers. So lots of sets that feel really big and feel like way bigger than the integers are actually the same size as the set of integers. So let's look at where we break this. So claim the real numbers has a fundamentally bigger cardinality than the set of integers. So if you're talking about all real numbers between 1 and 2, that's going to be the same as the cardinality of R, the set of all reals. In fact, just all the numbers between 0 and 1 will be the same as the set of all reals. And you can find a mapping by taking reciprocals. Alright, so let's prove that the reals have bigger cardinality than the integers. Not all numbers between 1 and 2 can be represented by fractions. For example, the square root of 2 is 1.414, etc. You can't write that as a fraction. We'll prove that in a week or two. So there's more real numbers than there are rationals. But let's prove that the real numbers are fundamentally larger than the set of integers. Okay? And we're going to do a proof by contradiction. So suppose that the reals and the integers have the same cardinality. In other words, you come to me and you say, hey Nick, I found a one-to-one map between the integers and the real numbers. All right, and I'm going to make it easier on you. Let's just look at, the set of all real numbers between 0 and 1. So a tiny little piece of the real numbers. And if you can map all the reals to the integers, then you should be able to map a tiny little piece of the integers. So you come to me and you say, hey Nick, I found a map between the integers and all the real numbers between 0 and 1. And I can prove that that's not true. Okay, so given some map phi from, and let's just go from the positives to so I don't know, the reals between 0 and 1. All right, here's what we're going to do. This is really easy and it's incredibly powerful. Right? You can take this and you can use it all weekend long. So let's see what your function maps some integers to. So suppose the number 1 maps to 0.426859973, something like that. And suppose your function maps 2 to, I don't know, 1/3. And suppose your function maps 3 to pi minus 3. And maybe it maps 4 to, you know, tomorrow's winning lottery ticket number. That's the Powerball, the 19. This is not Zeno's paradox. This is something a little different. All right. So every integer bigger than 0 gets mapped to some real number. And your claim is that, you know, for any real number that you think of, somewhere there's an integer that maps to it. That's what it means to say that you've got this one-to-one map between the positives and the integers. So you claim that any real number between 0 and 1 will show up somewhere in this list. And I can prove that is not the case. And here's how we prove it. I'm going to make a variable called b for bad. And it's going to be between 0 and 1. And here's how I'm going to construct this number. The first digit of b is going to be the first digit of this number plus 1. So I'm going to put a 5 down here. The second digit of b will be the second digit of this second number plus 1. The third digit will be the third digit of the third number plus 1, and so on. And, you know, if the digit is a 9, when I plus 1, I'll write down a 0. So this 5 will become a 6, and so on. That's a legitimate real number. It's between 0 and 1. And guess what? This number cannot appear anywhere in this table, because this number is different from every number in this table somewhere. Right? If we picked out the 100th entry in this table, the real number corresponding to that would differ from b in the 100th digit. Yeah, I could see a nice visualization to this. So here's a real number that cannot be mapped to from any positive integer. And that proves that you do not have a one-to-one correspondence between the positives and this set of real numbers. Since you cannot find such a one-to-one correspondence, we're forced to conclude that the cardinality of the set of reals is bigger than the cardinality of integers. Now that's you know, fairly deep and a little bit edgy and not something that you need to, you know, worry about for homeworks and exams and stuff. But it's a powerful technique, and this is basically called diagonalization. And it's a wonderful technique. It's useful for a lot of things. It's a huge monkey wrench, or wooden shoe if you like, that you can throw into something to really mess it up. And it's part of what happens when we try to prove that you can't solve something called the halting problem. It's part of what Gödel used in the early part of the 1900s to throw a monkey wrench into mathematical logic. It's part of what fuels a lot of the background research for cell matrix, the stuff I've been pursuing for a number of decades now. And it's a really simple argument, right? All we're doing is we're just adding 1 to the nth digit of the nth number, and we're making a new number, but by the way we constructed this, we can show this number does not appear anywhere in this list. And it's just a really wonderful technique. So that's a diagonalization argument. And it's a little related to the liar's paradox, or the way that Kirk defeated the androids that were working for Harry Mudd in an old TOS episode. All right, so that was our gear change for Friday. Have a good weekend. I'll post homework after class today. Take a look at that, so you can ask questions on Wednesday. And have a good one. Stay safe. Do something fun this weekend if you can, and I will see you next week.